Hi everyone, welcome back to the Linux. Today we are going to see about stochastic gradient descent. It is in a supervised machine learning used for a classification task, and it is in a linear classifier. When it's in a linear classifier, it will always find the hyperplane in the data points to classify its classes. For example, this is the graph, and it will always find the hyperplane to separate the classes. For example, this is in a class 1 and this is in a class 2. The hyperplane always looks like in a straight line or in a some 2D plane, and the equation of an hyperplane always looks like w1 x1 plus w2 x2 plus w3 x sorry plus wn xn plus b. The w1, w2, wn are weights, and b is called as base, bias or in a base. The stochastic gradient descent is in a not in a single algorithm, it is in a combinations of three algorithms, that is logistic, classifier, and SVM, support vector machine classifier, and perceptron classifier. It will implement these algorithms, especially in Python, and the only difference between these algorithms are its loss function. These are the linear classifier, right? All these algorithms are classifying its classes based on the hyperplane, or it's based on the hyperplane, right? It will classify the data based on this hyperplane. So all these algorithm are linear classifier, so it always separate the data based on the hyperplane. The only difference between these algorithms are the loss function and updating the its weights. For example, the loss function of a logistic loss, it's in a log loss. There is a function called as log loss. It will find the error or any losses in the unpredicted or misclassified data. And in SVM, there is called loss function called hinge loss, and in perceptron it will called as perceptron loss function. And stochastic gradient descent, it will implement all these three algorithms, and we need to tell the stochastic gradient descent which algorithm you are using, and it will based based on the algorithm it will change its loss function. And there is one advantages in stochastic gradient descent is minimum batch training. In these three algorithm, if there is in a data set like 1000, what it will do was it will find the error on each data point of all the data set. Like for the error for an error, or we can call it as loss for a data point 1 is L1, and loss for a data point sorry L2, up to loss for a data point of 1000 is L1000. What it will do was all these three algorithms initially find the loss for all the data. After the one epoch, this is called the one iteration of an entire data set called as one epoch. After the one iteration, it will sum them up, and it will find the average. For example, L1 plus up to an L1000, it will find the average. Based on the average, it will update its weights. In logistic and SVM and perceptron classifier, initially it will find all the losses for each data point, and it will find the average loss, and it will update its loss to its weights. But in the stochastic gradient descent, it doesn't classify the error for all the data point. How and it not only find the it only train small amount of data set. Sorry, it will only train the model using a small amount of data set. For example, if the entire data set or the size of 1000 or 10,000, it will take only minimum batch up to like 1000. It will take only, for example, it's only taken a 100 data set, like 1, 2, 3. In other other classifiers, it's always find the error for an entire data set and take the average, and it will update the weights, right? But in the stochastic gradient descent, it will only update its weights based on the single points. This means the it will find the prediction for a single data point, and it will find the loss, and it will update the weight on based on the one single points. For example, before finding this hyperplane, if I plot the point or plot the data points, it will looks like this. Before finding the hyperplane, this the entire data set will looks like this, right? If the data points are in a weight, this weight will update on each single point, right? If I draw the hyperplane after the classification, it will looks like this. The hyperplane always linear, and if there is some data point, the main drawback is if there is a data point, it is far away from these patterns. Actually, it will find some pattern, right? If there is a data point, it will far away from the patterns. These data points are called as outlier, or we call as noise, because we have some wrong data sets or wrong data points in our data set. These data points are called as outliers. The stochastic gradient descent, it will find the it will update its weights based on the single point. What if the model choose this data point and update its weight based on this data point, and the other weights are here, and these weights are far away from these weights are far away from these weights. In this case, it will lose some patterns in the data. So we use something called as regulations. These regulations are used to reduce the weight, or we can say as shrink the weightage near to n 0, not exactly 0, near to n 0. So the model or in a updating the weight will always average to its weights. I will tell you later in this video how it works. In simple terms, the other algorithms are update its weights based on the average loss in the entire data set, but in the stochastic gradient descent, it will update its weights based on the single point. Due to that, the dataset may have any outliers or any noises. So it will use something called as a regulation to prevent from the overfitting. And it is also in some one advantages like batch training. It doesn't need to in a large dataset to train the model. It will only need the batch model, batch dataset. So it will train the model and it can find the pattern in better manner. Why we use the S3D? It will compute the updates using a small subset of data, and its efficiency for in a large data set. Well, if your data set having a lakhs of data points, so it will only require for a thousands or 100 data points, and it will lower memory footprint. It's like in a large data set, right? We don't need to fully load the data set into our memory, so we will only need a small data set to train the model, and it can adapt the new data, and it will right it will adapt the new data based on the model trained, and using in a partial fit. The partial fit are nothing but we will train the model, right, up to a thousand. There are lakhs of data points, and partial fit are in partial. We can understand that there is only small data sets are taken in the entire data set. Mathematical formulation. the SDC minimize the regulation loss. The regulations or loss are nothing but it will prevent from the overfitting. Like if the data points, all the data points are near, if there is some data points are far away from this pattern, for updating this weight, it will, that the stochastic gradient descent, it will update the weights on based on the single data point. So for this data point, the update it will update the weight much larger than its pattern. So the regulation will helps this kind of problem to update the weights based on this pattern. What it will do was, it will, sorry, I will tell that later. These are the, we can call this function like loss function, sorry, cost function or objective function. These functions are used for an STD to minimize the regulation loss, fine, and L L is chosen for a loss function like ing loss, log loss, and perceptron loss. I will told you that there are three algorithms are used by a stochastic gradient descent. These are the three algorithms, and it will implement this. So we need to choose this function, right? Which algorithm is using, or we can say we need to choose which loss function we are using. And R of W in this equation is called as regulation term. I will tell you that it will solve these types of problem to overfitting. And based on there are two types, L1 and L2. Update rule. How it will update? I have already told that it will update its weights based on the single points, right? So if the single points are far away from our patterns, or it is in a noise, or it's an outlier, in the updating its weights, it's not good idea, right? For example, these are the entire data sets are here. If there is an outlier or a noise, will be here. If you are updating the weights based on this point, it's not a good idea, right? So the regulation, what will do was, it will find the average on the weights. For example, during the training model, it will find the hyperplane. The hyperplane, it looks like w1 x1 plus w2 x2 plus up to number of futures, that is n, w1 xn plus b. These are the weight w1, w2 up to n wn. These are the weight, and it will update the weight based on the single point. When what the regulation will do was, it will find the average on the weights. What it will do was, the regulations are looks like w1 plus w2 plus w3 up to wn. The n is number of futures or number of inputs, and it will divide by an n. It will give an average, right? And based on the average, it will subtract its value to its a loss function. For example, it will find some loss value is loss. This is a loss function. It will find some value, something called x. For if it find the loss value for this function, for this data point, it may be an outlier or a noise, right? So it will find the average weight on these data points, and it will subtract them. However, for if it will works for this data point, right? Because it's an outlier, its weights, this x, or maybe in a larger value, because it's an outlier, it has a large weight differences between these points. What about these points? In this case, for these points, it will always pull the losses near to zero, not exactly zero, near to zero. In these data points, or the data points not far away from the other data points, it will pull the data point near to 0. Because the loss functions also give some average value, because for this data point the loss function will be minimum and the average weight also will be minimum. So it's always pull near to 0, not exactly 0, and it will well works for the outliers or any noise. And these are the equations are used for an update function. These functions are will be differ for different algorithm. For example, the logistic having a different update function, and the SVM perceptron having a different update functions. In the formula for an regulation, the L2 called as the L2. There are two types, L2 and L1. The L2 formula looks like this, or L2. We can say that we will find the average, right? But in the L2, we find the square of its average. We will find the loss for an entire data. We find the weight differences between the data points. Sorry, not any difference. We find the sum of the square of its weight and divide by n. Here it will divide by n at 2. This is a regulation for an L type L2. For an L1, this is an equation. It will find the modulus. This means there is a weight which is lesser than 0. Lesser than 0, it will consider as a positive. So it will sum of the absolute values of its weights and find the average between average them, and it will update its loss. Sorry, and it will update its weights based on, sorry, it will subtract the loss to its regulations. If the it will find the misclassified data, sorry, it will find the loss for any misclassified data. The loss value is x, and it will reduce the regulation. This value are called as y, and we will update the weights equal to y. This is how it will update its weights and also prevent the some data points are far away from the, sorry, and some data points which is far away from the pattern. Advantages: it will scalable and memory efficient and online learnings. Scalable means we can choose the what algorithm you are using, like logistic or SVM or a perceptrons, and it will memory efficient because it will only trained or learned by a batch of dataset. The batch datasets are always smaller than the very smaller than the entire dataset, and it will be used for an online learnings, because during an online there is a streaming of data or incomings, so it will learn them by streaming dataset. Cons: and noisy convergence and sensitive to learning rate, because the learning rate, this is a learning rate, the learning rate are in the range of 0.0012 to 1. These are the learning rate. The learning rate helps to steps to converge the data points or steps to converge its hyperplane, and it will very sensitive in a learning rate and required future learning, and it will also escaping the local minima. Conclusion: the SGD update using the individuals or small batches of samples and flexible for loss functions, enable the various linear model like SVM, logistic, and perceptrons, and future scalings, and it will very depends on the learning rates, and regulation are critical because regulation used for overfitting. What is overfitting means? Overfitting means the overfittings are the model will works good on the training, but it will will sorry poor performance on the new data. For example, It is the pattern, right? How the overfitting occurs are all the some points are scattered, and it will, due to in a small data size, it will consider these data points near, consider these data points not as in a noisy or an outlier, and find the average between them, and it will affect our model to find the hyperplanes. If the data points, if it's considered a loss, it will the hyperplanes near looks like this. If it's not considered this is a noise, the hyperplane looks like this. During this, these data are not classified well. So to prevent this problem, the outfitting problem, we use something called regulations. I have already told that the regulations formulas, and when it find the loss of a data point, it will subtract the regulation with that, because maybe it's an outlier, so it will subtract it and it will update its weights. Thank you. That's it from this video. We will see